Hi, so I finally get to show you Phi. Just for context, so you know what's going on, you can see Visual Studio on the screen here, or at least the output window and a text file. Here's Visual Studio, got it on another monitor up here that so it can do its thing. When I hit F5, it'll just run. As you can see, it ran and it did nothing. It said run stop, which is just debug information. It did nothing because we've got an empty program. So that's good. It's being thrown together. It's not exactly complete yet. I am proving the point. It is not performant at the moment, but this is going to be the subject of ongoing research. However, the key principles I can show, I have enough running to show that. So I suppose a good place to start might well be, see if I move this here a little bit, it might well be the good old Hello World program. So how do you do Hello World in Phi? So this is not going to be too surprising, except there's this on begin. And, you know, at the moment I'm contemplating getting rid of the word on, but, you know, little adjustments like that don't really affect the core principles of the language. And yeah, it is a work in progress, but let's try I do our Hello World with a new line on it, and then when I try running this, I hit F5, and as you can see over here, it ran the program. And where you see these chevrons, I just have that at the moment to differentiate debug information from program output. So program output is being shown with these chevrons here, and so yeah, that's pretty straightforward. What this is saying effectively is when the program begins, print Hello World. So if you watched the previous videos, you'll remember that I was talking about the Hello World program in imperative programming languages as actually having state, because there's a program counter which goes and executes, you know, enters the function, executes what's in the function, exits. None of that happens with Phi. Here we're basically saying what we want. What we want is for Hello World to be printed when the program starts. So, okay, and you might say, well, that's all very well and good, but what would happen if I said, you know, get it to print something else? So what do you think will happen? I don't know, never tried this before. It's Hello World Foo. Because, yeah, it's going to do that. Now, the thing is that this is something is a little bit of a concern for me at the moment, but if I go and swap these around, I wonder if it would, yeah, it's misleading. Because if it was deliberately to do foo first and then Hello World, then that would be a program counter, wouldn't it? It would be, no, it would have to remember that it had printed foo and then it needs to print Hello World. It would be, thing is, that is non-deterministic. It's undefined in the Phi programming language. You're not supposed to do this or rely on it. Basically, you're saying when the program starts, do these things, but there is no order indicated. So just bear that in mind. I'm not going to go back to just Hello World by itself. You'll see this will become clear in a minute as to why it's done this way. So that's fantastic. But maybe you want to do a little bit more than just print Hello World. So why don't we have a variable? I tell you what, let's print A. So if I do this, I'm basically saying when the program begins, print the value of A. And as you can see, we have an error. It's undefined value A. Well, okay, I tried to print A, but I haven't defined A. All right, so let's define A. We'll see. So what I'll do is I'll go and say on begin A equal 10. So, all right, So what I'm immediately showing you is how this differs from ordinary languages, okay? Because this is, you've got to forget about the program counter. This is not imperative programming. You need to forget about imperative programming. That's the whole point of phi, is it is not imperative programming. But unlike functional programming, it embraces state. So what do you think is going to happen here? If you were suspecting it was going to say undefined value, congratulations, because that's exactly what's happening now. You'll go look at that. You might say, well, you said what A is, and then A is right. Because, right, the order of instructions are unimportant. This is exactly the same as this. I can, right? Because all I'm saying is that the moment the program starts running, I want to print the value of A. And then I set the value of A to 10, or I set the value of A to 10, right, after the event of the program beginning. You could almost think like this is event driven, sort of. In principle, yes, but with a twist. So the reason why A is undefined right here is because at the moment when the program started, A was not defined. And what we do is define A when the program starts, right? So logically, it doesn't exist yet. It will. Okay. Well, how are we going to print A? And so then we see the essence of the phi language start to become clear. On change A, print A. So you can see where this is going, right? So what we have here is that we're basically saying that when the program begins, we set A to 10. And when A changes, we print it. And so these are two rules. So it's like whenever the program starts, it will always set A to 10, and whenever A changes, it will always print it. And so the result is when I run this, we should hopefully see it work. There it is. It's gone assigned a 10 to A. It's debug information there, so we can see that an assignment occurred, and then it printed A, which had a value of 10, and then it stopped. And as you can see, we're kind of missing a little bit of this action here. Now, as I'm doing this, it's possible I do something that isn't currently implemented. We'll see. I've got a suspicion that it will not put a new line after mar 10. I'll get some kind of error. We'll see. Oh no, it worked. Okay, so that's covered. Oh, that's nice. As I'm building the language up over time, there are a lot of combinations of operators and types which are not implemented yet. And what I do is I implement them as I find them, you know. So, okay. Now, hopefully you've got the picture here. When the program begins, A is set to 10, and when A changes, A is always printed with a new line. That's what this program is. It's basically you say what you mean in the language. You know, as I pointed out in the previous videos, right? Imperative programming, it doesn't really represent meaning very well. This is so. Okay, so what I'm going to do then is move this line here. So again, you look at this and you go, oh, I'm going to try and print A before it's defined. No, because the order of the instructions is totally irrelevant. This is the same program, and this is one of the rules in the definition or the design of phi, is that the order of instructions should be always not relevant. You can say that when it's executing expressions, the order is relevant, but that's a mathematical expression. It's not anything to do with state. So there is a subtle difference, but very important difference there. So if I try running this, it just works anyway, because it isn't the line number doesn't matter, because there's no program counter. So what we're basically saying is, and A is set to 10, when A rather is changed, we always print it, and at the beginning of the program, you know, we always set A to 10. And if I go and I can change this to something else over here, and then of course it should just work, right? 99. And then we print it. Okay, but you know, not necessarily going to be all that useful yet. All right, and you know, great, but what about loops? What about let's see if we can print the numbers 1 to 10. All right, so that's my next challenge here. I want to print the numbers 1 to 10. I don't know if you can see how you do it, but you know, first of all, I'm going to set a equal to 1, and so it will print. Right, now you might be thinking, I need to put it into a loop. I need a while or for. No, there are no whiles. There's no while. There's no for. There's no if. There are no control statements at all, because if I was to introduce control statements, then I'm bringing back the program counter, and I want to get rid of the program counter. Never mind, the go-tos are evil. This madman here is basically saying program counters are evil. I mean, if you think about it, the go-to is implicit between every instruction in an imperative language. There is an implicit go-to next line. So let's get rid of the go-tos completely. Okay, how do we do it? Well, we can indicate what we want done when there is a change to A. So why don't we just add this? On change A plus plus. And so what happens now? Can you see what happens? All right, let me run it. I'll run it. Here we go. And as you can see, it looks like a loop, doesn't it? But it's a loop without any program counter. It's going to go on forever. Well, yeah, it will go on forever. So maybe you want it to stop. So yeah, well, maybe you can see how we would do that. I've got to clear my throat, so I should have edited that out on the audio. So anyway, what we want to do is perhaps have the thing stop when it reaches 10. Okay, so how can we do that? Well, okay, I don't know if this is going to work, but there is an instruction I've added here, is on change, we could say finish, couldn't we? Well, we need to do something with a comparator, right? The easiest way to do this is the following. Now, I have a when statement. There are a few ways, but I have to go with a way that works in the language as currently implemented. But it's like on change A, then we're going to introducing the when. Now, the when is a bit like the question mark colon operator in C. It's basically a mathematical expression. So it's as close to an if statement as you're going to get. But it isn't really an if statement because there's no control flow. So I'm saying when A is less than or equal, no, I haven't implemented less than or equal to yet. When A is less than, I think it works anyway. When A is less than 10, let's try it like that. When A is less than 10, then A++, wend. A bit ugly, the wend, I might change what that means. But basically, this is saying when A changes, then if A is less than 10, then, oh yeah, that will work. If A is less than 10, then increment A. Okay. If you're used to C++, that would be basically saying the same thing as this. Except it isn't, because you need to have like both. Yeah, so it is an action. It's an act, because the way that this works is that you've got basically a trigger and an action. Each rule has a trigger. This is like a begin. The trigger here is when A changes, And well, yes, you're allowed to only execute this when A. So I suppose you could translate this to when A changes and A is less than 10, then A++. Does that make sense? So it's a rule. Let's see what happens if I run that. And it's there. It is. It's printed all the numbers from 1 to 10, and somehow it just stopped. How did it know to stop? And what about, you know, the order of the instructions? How do we know? I mean, it's like if I do this, right? So there it looks like it's incrementing A before it's printed, but now it's thinking imperatively again. That will make no difference at all, because there is a special way or a specific way in which variables work. The variables are immutable for any execution rule. So a way of thinking about how this works is that you have your state. For example, the variable A is a piece of state. You have your state, and when an event happens, in this case it begins with begin. When the program begins, the state is modified by the begin statement. Okay, but that state that is the input state to the begin, right, is not modified during the execution of begin. Similarly, the A is immutable during the execution of A, or execution caused by a change in A. And the way that works is the output of the changes that occur from the triggering of rules is buffered. It doesn't immediately modify A. What happens is that all the rules for a current event are executed, which generates new values of the state, and only after all the rules have been applied does it copy those results back into the state. So the end result is that the order really doesn't matter, because the way to read this is when A changes, print A, but when A changes, print the value that A changed to at the moment when it changed. And at the same time, at the moment that A changed, we prepare the new value of A. In effect, if I was to, I think I can, with the current language, do this, A equal A plus 1. Let's see if this actually works, or if there's it doesn't like that one. Unhandled left value type, integer for plus. So yes, we have a little bug there, but no matter. I could probably show it in a different way. But basically, if I did A equal A plus 1, that's the same thing as A plus plus. And so in this instance, it's really doing something like A prime is the next value of A, right? Is or you know, A next equals the current A current plus 1. And so that's why it doesn't matter what order you put these things in. It's order independent. So there you go. We're able to print. So yeah, it looks like a loop, but actually it isn't. Well, it's not as we know it. What about how it knew to stop? Well, basically, when a rule is executed, or a set of rules are executed for a change in state, for example, at the begin, which is counted as a change in state, then, as I said, all new values are prepared, and then those values are copied over. But if there is nothing to copy over because the state hasn't changed, that is, if any execution or check on rules to execute results in no change in state, then quite logically there will never be a change in state in the future. So it picks that up and terminates. So this is how this manages to exit already. Basically, once the value reaches 10, then at that point this doesn't execute anymore. And because it doesn't execute anymore, A is not changing, and because A is not changing anymore, there is no state changing. The program is now complete. So that is the basic principle. In summary, right, you take your state, an event occurs, that event is matched against a set of rules. The rules change the state, or prepare the change of state, I should say, until all the rules have been executed for that change, for that state change. Then the new state is copied over to the current state, and if there has been any change to the state, that is actually strictly any rules need to be executed, would be a better way of looking at it. If upon copying over there are any rules that need to be executed, it will then execute those rules. And again, copy over the state and keep doing this until there are no rules triggered anymore, in which case the program is able to terminate. Okay, so let's go a little bit further. I'm going to demonstrate a function, because you can't really have a programming language without functions. So yeah, here's a function. It's going to calculate a square root. If you're using a procedural language, you could call this a pure function, because there's no state that is modified by this. All right, so this is the equivalent of a pure function. In fact, the variables which are indicated here, we have v, g, well, there's only two actually, v and g. They're both local to this function. Okay, so all I've done is I've said function, the name of the function, and I'm saying it takes a variable v. Although variables are typed, there isn't any strict typing at the moment. I don't know if I will have that or not in the language. This is to be decided. It will execute this function with its own virtual machine, with its own machine to execute this, with the same rules that I just described. When the state in this scope no longer changes, or there is an instruction to actually force an exit as well. So if it doesn't, until it exits, it's going to keep executing. When it's finished, then it will actually execute or exit the function, and there is a mechanism for passing a result to the calling function. So let me just try and do here on begin, and we'll do print 9, and I'm just make sure everything's working. So what we should do is that we see 9, but let's also add a carriage return or line feed character in there. So so this function appears to have done nothing. In fact, it's actually read it and prepared it, and we can use it. What does this function do? It calculates a square root. Now, of course, there's no real practical reason why you should write your own square root function, but this is done as a demonstration. It's a very simple algorithm, and it's to prove that I can use this language structure or architecture in order to execute algorithms. Okay, it's a simple one, but this is early days. In reality, I would, under the hood, call the maths function maths library of the language to give you the square root. But okay, so what I'm going to do now is just do on begin a equals 9, and then we're going to print. So it's the same thing that I had before, I guess, but we don't do that on begin. It's on change of a print. Okay, so let's see how that works. Is that okay? And we actually have an error. On begin, a equals, because I put a semicolon in. There's no need for semicolons. All right. I mean, I might add the option later. But so what we have is 9 was assigned to A, and then because A changed, A is now printed. Okay. What I want to do now is actually get the square root of 9. So what this is now going to do is say, when the program begins, put the square root of 9 into A. And what the machine does at that point, it goes, square root? What's square root? Square root's a function. Okay, well, we need to, spin up a virtual machine for handling this square root calculation. So, you get your own, there's a kind of a local context here, local scope in order to do that. And it's going to call this, and it's going to assign 9 to V. And then it will operate the algorithm. We'll look at the algorithm in a minute. And as you can see, it did actually come back with the answer 3, which is a relief. And you can see some intermediate steps in here where it's basically printing any assignments to variables. Let's have a look at that a minute. You can see that it assigned the argument 0, which had a value of 9, this debug thing, to V. And so basically what happened is, upon this being requested, it put 9 into V in the local scope of the execution of this function. And then it seems to have, again, it looks like a loop, right? It seems to have iterated on the value of G until G didn't change anymore, at which point it assigned the result of the square root calculation to A, and then because A changed, A was printed. And that's what you've got. So let's look at how this actually works. This is Newton's method for using Newton's method for calculating a square root. And the first part here, it takes the value of V, which in our example here is 9. It divided it by 2 and assigned it to G, which we can see happen on here. And then it says, when G changes, then calculate a new value of G. And this new value of G is given by this formula. This is from Newton's method. G plus V divided by G, all divided by 2. And so you can see that's what's happened here. There are no other rules to execute. This rule here says on finish. Well, we haven't finished. That hasn't happened yet. But having executed that and got ourselves this value here, G has changed. So we better check and do it again. And so now the rule that we need to execute again is G. And so executing G gives us a new value. And it keeps doing this until eventually G is 3. And when G is 3, it calculates a new value of G, which is 3 again. This has resulted in no change. Therefore, because G has not changed, there are no more rules to execute, and the program finishes. And there's a little step I put in here, which, I'm not entirely happy with that, but I will look at it again. But for now, when you can say that on the finish of the program, in this case it's a small program here, the end of the function, right? On the finish of this, then return G. And so what it's doing is taking that value of G and assigning it into a temporary place that can be used by the language to assign it. All right, so it basically stores the result. Then this is finished executing. We're back to this program now. And we were actually just still executing this on begin rule. It assigns the result of this calculation to A, which is what this thing is here. And then there were no more things to execute for begin. And all that's finished. And now it looks and says, do we have anything to execute? Well, A changed. We have a rule here that when A changes, we should print it. So we must print it. And so we do. And then it says, are there any other changes? Answers no. And it terminates. Stop. And that's what you've got. Now, I do realise that this might, I don't know, you can tell me. I'm really interested to see if how easy it is to get your head around that. because it's, in terms of programming, you've got to think in a different way to the procedural. I'm also interested to know if there are other languages out there that already do this. I looked, and I'm not really an expert in all programming languages, so I wouldn't be surprised if this idea is not entirely new. But what I've done is I have taken the idea and created an interpreter, and I believe it is entirely possible with this language to do anything. This is something I'm going to subsequently prove, and I'm pretty sure as well that it is also going to be useful. Why it's useful and how it can be used, especially in video game development, comes back to that question of concurrency. I hope that you can see that by removing the program counter from the process, and being able to state what you want to have happen when something happens, that's basically the executive summary, right? You can tell it what to do when something happens, where a happening is a change in state. So any change in state can trigger a change in state. This is in effect what you do all the time in video game programming, where you're dealing with concurrency. It's really fundamental. And when you look at programming in Unity, for example, and you start using your coroutines and so on, in the end, those coroutines, the most useful thing for coroutines is waiting for something to happen. So in a sense, this language takes that waiting for something to happen and you specify what you want to do, what problems you want to solve, and how you want to implement your algorithms in the basis of when things change. And so in this way, with no program counter, with no order of execution issues, the theory is you'll end up with much more robust code, and that it fixes a huge bunch of problems, ranging from just concurrency in a single thread to multi-threaded programming, to correctness, program correctness. Alan Turing's famous paper about the halting problem proved that a computing, at least imperative computing device, could not run a program. You could not write a program that was able to test the validity of other programs. Okay. It's probably also true when you're thinking in this paradigm, but because the language here is always expressing intent rather than instruction, I think you get a lot closer. I think there's a lot more potential for proving correctness of a program when you're in this domain. So lots more exciting things to cover. My intention is to continue building up the language, trying out other algorithms. It's a bit like programming all over again, right? At least for me. Then also rolling it into a video game engine. Perhaps Unreal would be a good choice for this one, as I've written this thing in C++. And so there you go. And I'm hoping to stream development of this, or continuation of the research into the Phi programming language in the future. Okay, I hope you enjoyed that. I found it at least a little bit interesting. Take care, everybody. See you soon. Bye.